Information that we're covering today in section 4 is not included on the quiz tomorrow. So my priorities tonight would be, if I was planning to do anything from that extra review that I gave you yesterday, the quiz review, I would work on some of that, check my answers on the answer key online, and then do some of my complex number homework. Okay, so this stuff will not be included on the quiz. Complex numbers we introduced last year for the first time. They're the numbers that have that imaginary unit. Okay, so before that moment, we only knew about real numbers, and then we said, oh, there's actually these numbers that aren't real. Cool. Does anybody remember what standard form for a complex number looks like? Always write them as A plus BI. A is the real part, because it doesn't have anything imaginary, and BI is the imaginary part, because it has the imaginary unit. Does anybody remember what I is equal to? The square root of -1. So you should have had a discussion last year about, like, what number multiplies by itself to give you -1? No number exists, because same signs multiply to give you positive numbers. So mathematician says, if I was doing the square root of -1, I'll just call it I, and it can hold a place, okay, while there is no real number there. Complex numbers, then, are the biggest set of numbers that we know, and that's split into real numbers and imaginary numbers. So know that all the numbers you know, like 1, 2, 3, 4, 5, are really complex numbers. They're just in the form A plus 0i, right? So 1 plus 0i, 2 plus 0i, 3 plus 0i, they are complex. They just have no imaginary part. And then anything that has a b value not equal to 0 becomes imaginary. So complex does not necessarily mean imaginary. They can be real. Then you should have, at some point, talked about the cycles of I. Now this is a brief moment in Algebra 2, so we don't spend a whole lot of time on it. But basically, as we raise I to different powers, we're going to run into 4 different cycles, and then it just repeats itself over and over and over again. So I'm going to start with the lowest exponent, I to the 0. And tell me, if you raise I to the 0, what would you get? 1. Because anything raised to the 0 is equal to 1. Okay. So anything in that iteration is going to be equal to 1. I to the first is really the square root of -1. But in terms of I, that's just I. Okay. So I to the first is equal to I. Imaginary unit. What would happen if you did I squared? -1, right? So you could think about it like, okay, I squared would be like the square root of -1 squared. The square would cancel out the square root, which should essentially give me -1. Okay, so far my cycles start at +1, go to positive I, go to -1, and if I were to do I cubed, the way I think about it is, do you agree that I cubed would really be I squared times I? What's I squared? -1. And -1 times I would just be -I. Okay. Now, if I multiply by another I, so if I were to do I to the 4th, then -I times I would be -I squared, and -I squared would be -1, which will get me back up to +1. And I multiply by another I, and I go to I, so that'd be I to the 5th, I to the 6th, I to the 7th, I to the 8th, I to the 9th, I to the 10th, I to the 11th, I to the 12th, right? So it's just going to go in these 4 cycles. This is the only 4 things it can be. Okay? Here's how you're going to work to simplify things. Okay? Divide your exponent by 4. match remainder to cycle of I, and simplify. So we can do high powers of I using basically the remainders because we're going to run in these 4 cycles. So that's why we're going to divide by 4. If you've ever had any experience with something called modular arithmetic, this is a great example of when we only care about the remainder, not actually the quotient in division. So we'll start with an easy example of simplifying. If I give you something like 2i cubed plus I squared, I need you to simplify that so that it looks like a plus bi. In a plus bi, the highest exponent for I can be 1. So we need to get rid of this I cubed and I squared. Based on our cycles of I cubed is really equal to negative I, so I can do a substitution. That's 2 times negative I. And I squared is really equal to negative 1, so that's plus negative 1. And that's negative 2i minus 1, but I want it to be in standard form, so I got to put the real part plus the imaginary part. So I'm just going to switch those around, and that's going to be negative 1 minus 2i. So always write them in the standard form. Real part, imaginary part. Sometimes I'll make the exponents higher. And I don't expect you to go through all 25 and figure out which one it lands on. I want you to think about what would that remainder be if I divide it by 4. That's going to tell me which cycle of I it matches with. So if I'm doing 5i to the 25th, 25 divided by 4, it'll go in 6 times. What's my remainder? 1. So this is really like 5i to the 1st, which is 5i. Over here, I've got to think about 3i to the 74th. Now, if you had a calculator, you could go in and see what numbers divide by 4. To make this easier for myself, I know that 80 is divisible by 4, right? That's close to 74, so that's got to have a remainder of 0. If I backtrack, 76 is also divisible by 4, so it has a remainder of 0. That means 74 has a remainder of 2. Okay. So this is really plus 3i squared, which is plus 3 times negative 1, and then do that piece where you make it look like a plus bi. So it would be negative 3 plus 5i. So it's mainly figure out which cycle of I it is, and then do the substitution. The highest exponent in your answer for I should be 1. I the first. You shouldn't have any I squares or I cubes. Does anybody have any questions about that? Yeah, Macy.
So how did you get 5i to the first?
Because 25 divided by 4, I would be able to get 4 in 6 times with a remainder of 1. There are only 4 cycles, so you're always going to divide your exponent by 4. Because it's going to repeat every 4. Remember, this is I to the 0, I to the first, I squared, I cubed. I to the 4th, 5th, 6th, 7th, 8th, 9th, 10th, 11th, 12th. And once you do that a few times, you realize it always goes back to 0 when the number is divisible by 4. So you're really working with the remainder. Okay, last thing we want to talk about, and then you'll run through some examples, are complex conjugates. Complex conjugates. Complex implies of the form a plus bi. Conjugates in math are 2 binomials that have the same first and last terms, but they differ by signs in the middle. So complex conjugates, if you have a plus bi, then a minus bi is its conjugate. Don't change the sign of the real part, only change the sign of the imaginary part. Now, you're going to see when you do some of your examples, when you get to division, it tells you to multiply by the complex conjugate. So I'm just going to show you, in general, what should always happen when you multiply complex conjugates. So let's take the two conjugates, a plus bi times a minus bi. Those are conjugates, and this is what you're going to do in the division problems. If I FOIL this out, okay, so distribute and multiply, a times a would be a squared. To do a times negative bi, that's positive times negative, so it's going to be a negative. And then I always write, when I have lots of letters, just in alphabetical order, so I'm going to say abi. The next piece would be positive bi times a, which will be positive times positive, so now it's plus. And bi times a, I'm going to put in alphabetical order, abi. Multiplication is commutative, so it doesn't matter what order you multiply those things. And then the last terms would be positive bi times negative bi. A positive times a negative is a negative. B times b, I times I, b squared, I squared. What do you notice happening in the complex conjugates? That's going to be helpful. Minus ABI, plus ABI, cancel out. So if you choose conjugates, the I terms will always cancel. And then what you have left over is a squared minus b squared times I squared. I squared is really negative 1, so that's a squared minus b squared times negative 1, which means when you multiply complex conjugates, you always come up with a real number, a squared plus b squared. It has no I in it anymore. Real number, yay. Now, you can choose. You want to do this work every time when you multiply complex conjugates, that's great. You can do it, and it'll always work out to be this thing. Or if you like patterns, and you like knowing those things, you can skip right down to a squared plus b squared. So in number terms, if I had 3 plus 2i, and I multiplied it by its conjugate, 3 minus 2i, I know that that's going to be 3 squared plus 2 squared, which is 9 plus 4, or 13. Now, I can do all the work and see the i's cancel, but that's always going to happen if they're conjugates. So I can jump ahead if I want. So what I'm going to ask you to do for the rest of the period is take your notebook, consider this part of your notes. You're going to go around to the stations in the room, and you're going to try to do a few of those examples. Now, I would say try to do some of A through E first. So like A and B are adding and subtracting. C, D, and E are all multiplication. And then F and G are division. So I wouldn't start with division. I'd do an addition and subtraction or some multiplication and then try division. And I'd say you probably need about 2 or 3 minutes per problem that you do. The answer's on the back, so you can check to see if you're right. If you're having any difficulty getting the right answer, please call me over to wherever you're working. I'd be happy to help you. You can work in pairs or trios. You can get up out of your seats. You can go to the ones on the wall. You, of course, have one at your pod right now. Okay. And you don't have to go in order, A, B, C, D, E. You can skip around as you want. Write anything that you think would be helpful in your notes. Okay, so if you need a hint about dividing complex numbers, write down what that hint is that you'll need to know.